today we will finish this particular lesson on confidence intervals. Then we will go into hypothesis testing, and we'll finish that. And we'll for one sample test, and there's another one in two sample tests in lesson 10. So we'll do that as well. So there's a lot of content to be covered today. And next week, which is I think the last week that we'll be meeting, so there we'll look at next week we will look at ANOVA and chi-square. Today is a very heavy day with the content at least. So uh, all of this is recorded and put on the YouTube channel as well. So you can right. So let's get to our lesson on confidence intervals. So I think under confidence interval estimation, um, we looked at first, just to give you a quick highlight of what we did. We talked about confidence intervals first for the mean, and under confidence interval for the mean, we looked at two areas. One was when the population standard deviation was known. The other scenario was when the population standard deviation was unknown. So when the population standard deviation was known, um, when the population standard deviation was known, when the population standard deviation was known, the confidence interval was the point estimate. Um, Here it should be, because I'm using the tab, it's not showcasing here, but should be x bar plus or minus um, z alpha over 2 times sigma over root 10. That was the equation when sigma was known. So what was this x bar? This was your point estimate, and this was your sigma over root 10 was your standard error in this context. And then this was what we used for sigma unknown. When sigma is known, which is the z distribution, is what we used. So sorry, when people are joining in, I think it's not muted, so I have to mute them also. That's why there's like, okay. So confidence interval for mean is what I was talking about for those who just joined in. Just a quick recap. Under that, we looked at sigma known, that is the population standard deviation is known. The second scenario was population standard deviation was unknown. So for the equation that we used in this scenario of population standard deviation being known was this equation over here, x bar, which is the point estimate, which is also your sample mean, plus or minus z alpha over 2 times sigma over root 10. But when so we looked at an example here as well. So I will not go into that again because the solution was given and we did it last week. So I would urge you to go through it. When sigma is not known, which is the more practical scenario, the confidence interval then was given as where, since sigma is unknown, we don't use z, we use the t distribution. So the confidence interval then was same point estimate x bar plus or minus, instead of z we use the t distribution times not sigma, s over root 10. The sample standard deviation is what we used because sigma is, or the population standard deviation is, unknown. So the key factor, that the key changes are here we are using the t distribution and sample standard deviation is what we are using. So I think we looked at an example there as well. So here the difference when you're using T distribution is you're introducing something called the degrees of freedom, and that is key. So degrees of freedom. So the degrees of freedom is basically your sample size minus one in this case, in this particular case. So we looked at all of this last time as well. And in terms of the two distributional tables, how it would look like. So you have the T table like this. So here you have the degrees of freedom up to going up to 1,000, and then it approximates to Z. Because we talked about it, when the sample sizes are very large, the T distribution approximates to Z. And on your rows, you have the the alpha values, right? So if I say confidence level of 90%, what that means is that is equal to 1 minus alpha. So alpha is 0.10 because this is 0.90. So alpha is 0.10. If I say confidence level of 95%, that is 1 minus alpha is 95, which is 0.95. So alpha is 0.05. Then what you have here on top is whether the particular distribution is a one-tail test or a two-tail test, right? So we'll get to that as well. I think we looked at a few. Um, the important thing in a T table is that all these values that you see are they're not probability values, because in the standard normal distribution table that you see, all of these are probability values. All of these values are probability values. So that's important. That's an important difference there. Right. So let me just get rid of all of this. Okay, going back to the lecture, just a quick summary of what we've been doing. So I think T distribution also we went through it. We looked at an example as well. Now we come to confidence interval estimation for proportion. Confidence interval estimation for proportion. Right, which is the next part of it. So in this case, what we are looking at, the logic is more or less the same. So here, the standard deviation or the standard error is the population standard error is given by pi 1 minus pi divided by n. I'm pretty sure it's correct in your when you download the presentation. It's just because on the tablet it's not shown. But we estimate this particular error using this particular equation, right? So the standard error is estimated using this particular equation. And what is the equation for the confidence level? You have P plus or minus Z alpha over 2 times the standard error. See, because its confidence interval is always the point estimate, which is P plus or minus. In this case, we are using under proportions. When we are looking at confidence interval for proportions, we are using the standard normal distribution. So you have Z multiplied by the standard error. So the standard error in this case is estimated by P times 1 minus P divided by N. Now, what is P? P is the sample proportion that we are using. So proportions. Only thing is there's a small caveat, which is this over here. When we are looking at an example, you must always do this, which is you have to calculate the sample size times the sample proportion and see whether it's greater than 5. And you have to calculate the sample size into 1 minus the sample proportion and see whether it's greater than 5. You have to see whether these two conditions are checked, because only then can we use the Z distribution. And I've given you the reasons over here. Now, if we look at this particular example, What are they saying? They're saying a random sample of 100 people shows that 25 are left-handed. So, uh, and they're saying form a 95% confidence interval for the true proportion of left-handers. So before we get into the calculation, what do we have to do? We have to check whether NP is greater than or equal to 5. So N is the sample size, which is 100. Proportion, P is the sample proportion, 25 divided by 100. Left 25 of the people chosen are left-handed. So this is 25, which is greater than 5. N times 1 minus P, N is 100 times 1 minus 25 over 100, that is 75. That is also greater than 5. So those two conditions are met. Then the confidence interval for the true proportion, which is given by pi, is equal to P plus or minus Z alpha over 2 times the standard error, P times 1 minus P over square root of N. So what is the sample proportion in this case? It's 25 over 100 plus or minus Z alpha over 2. So before I write this equation, let's figure out the particular parameters that we have to figure out. So P is 25 over 100. That's fine. So we are told to make a 95% confidence interval. So 95% confidence interval means 1 minus alpha is 0.95. Therefore, alpha is 0.05. Um, and therefore, alpha divided by 2 is 0.025. Therefore, Z alpha over 2, which is Z 0.025. What's the 0.025 of Z? Let's go to the distribution table, not T. I want to look at the standard normal distribution, and I want to look at where 0.025 is. 0.025 is over here. 0.025 is over here. So that is 1.96, right? So therefore, I say my Z 0.025 is 1.96. So then I just simply go and substitute in the values for the confidence interval of pi. So P is 0.25 plus or minus, because I had to have an interval. Plus gives me the maximum level, minus gives me the minimum level. Z is 1.96 times P is 0.25, 1 minus P is 0.75 divided by N is the sample size, which is given to us as 100. With, from which I get the answer for pi. So the maximum value of pi is 0.3349 and the minimum value is 0.1651, but we asked for an interval. So pi lies between 0.3349 and 0.1651. This is the confidence interval that we are looking at. Right, so this is the estimation. So we are 95% confident that pi uh, is between these two. So how do we interpret that? We can either say 95% confident that the true percentage of left-handers in the population is between um, these two values, that is 16.51% and 33.49%, or you can say 95% of the intervals formed from sample sizes of 100, 95% of the intervals formed from sample size of 100 will contain the true proportion. That is what we are saying. So that is an example of sample proportions. I've given another example over here. So if we take a look at this example over here, so what are they saying? They're saying a smart home technology company wants to estimate the proportion of its customers who are satisfied with their purchase. To do this, they conducted a random survey of 200 customers. Okay, n is 200, and found that 140 of them reported being satisfied with. So I'll say sample proportion P, which is defined as, I'm calling them the people who are satisfied out of the people surveyed, 140 over 200 with the product. The company management wants to construct a 95% confidence interval. So 1 minus alpha is 0.95, therefore alpha is 0.05, therefore alpha divided by 2 is 0.025. Hence, I don't need to look at the table again. This is plus or minus 1.96, the Z value. Okay, 95% interval for the true proportion of satisfied customers. That's why I take simple PS defined as the uh, proportion of satisfied customers, because it's asking me for the proportion of satisfied customers. Um, right. So I'm asked for the confidence interval here, P plus or minus Z alpha over 2. Remember that. That's a mistake that one can make. Standard error is P, 1 minus P divided by N, square root of that. So P is 140 divided by 200, plus or minus Z is 1.96. 140 divided by 200 into 60 divided by 200. 60 divided by 200 divided by N is 200. Don't forget the square root. So you will get two values here. Here you will get the plus value, and here you will get
Yeah.
the uh, sorry. It's great if you guys can mute. Just check whether your mic's on mute. So coming back, that's all it asks, right? So it's like I said last time, it's more or less a very mechanical pattern that you see, but there are places then what that where one can make mistakes. Most important place is over here, which distribution table. Now remember, I'm giving all the equations. So when you read the question, first and foremost, you need to understand, okay, what is it asking? It's asking for proportions, right? So then you come to the question, okay, on proportions, what are they asking? Um, Confidence intervals, right? Right. So confidence interval on proportions. So quickly, you turn to the page where it has equations. You note this equation down, and you make sure that you look at the right table, right? Because uh, when you finish this lesson, you will have three tables: the standard normal table, the T table, and the F table, right? So you make sure that you look at the right table, and you make sure you get the right equation. That is key. That is one place that one can make a mistake. But if you get all of this right, and maybe you make a small mistake here, I mean, very few marks, about half a mark can be reduced because everything is right. So that's on sample proportions, and that from that we come to an end. I won't go into this part, this section over here. So under confidence interval, we looked at two main things. We developed confidence intervals for mean and confidence intervals for proportions. And when we are talking about confidence interval for mean, there were two scenarios: when sigma was known and when sigma was unknown. When sigma was known, what was the distribution we used? We used the standard normal distribution, right? And what was the confidence interval that we used for mu? X bar plus or minus z alpha over 2 sigma over root 10, right? When sigma is unknown, we use the t distribution. Sigma is unknown, we use the t distribution, right? And in that scenario, the confidence interval is same thing, x bar plus or minus. Here we are using t alpha over 2, which has the degrees of freedom s over square root of n. In the case of proportions, we use the standard normal distribution, and I've given the reasons as to why we use it in this lesson as well. Um, and the equation that we used for pi, which is the population proportion, the confidence interval is point estimate, which is sample proportion P plus or minus Z alpha over 2 because we're using standard normal distribution. Standard error is given by P1 minus P over square root of n. So the standard errors for sigma known under the confidence interval calculating for mean when sigma is known, standard error is sigma over root n. When sigma is unknown, it's S over root n. When sigma is known, we use the standard normal distribution. When sigma is unknown, we use the t distribution. Under confidence interval for proportions, we use the standard normal as square root of p 1 minus p divided by n, and the table that we're looking at, or the distribution we are looking at, is the standard normal distribution. So those are the three things. So that brings us to an end of our eighth lesson, confidence interval estimation. So from this, we go into um, a very important lesson, which is hypothesis testing. Hypothesis testing. And here we are looking at first one sample test. So we are only taking one sample because the next lesson that we are covering is hypothesis testing for two samples. So here we'll first look at the one sample test scenario case. Um, so we'll be looking at what is a hypothesis. That's the first thing that we'll look at. Then very briefly, we'll look at types of errors in hypothesis. There are two errors, type 1 and type 2. And the hypothesis tests that we're going to do is for mean and for proportions, same as for confidence intervals. So confidence interval, the concept of confidence interval, the concept of sampling distributions, all of that is used in hypothesis testing. So when we talk about what is a hypothesis test, the most important thing to remember that a hypothesis test is a claim that one makes. It's a claim made on the on a population parameter. That is very, very important to keep in mind, right? So, for example, you can be making a claim on a population parameter like population mean. So we are saying uh, the mean monthly cell phone bill in the city is $42, or you can make a claim on the population proportion. Population, the proportion of adults in this city with cell phones is 0.68, right? So that's what I try to highlight here. It's very, very important that you understand that we are making claims on the population. So here it should be equal to, what I'm trying to say is we are not making claims on the sample, not about the sample. We are making claims about the population, because these small things in the midst of all this information, you can make mistakes. Hence why I am emphasizing on this fact. So when you take a hypothesis, there are two hypotheses that we note down. One is the null hypothesis, which is H naught. This is called the null hypothesis. And the other one is the alternative hypothesis. Alternative hypothesis. The recording for this is also available. I made it available. So the null hypothesis is you kind of begin with the assumption that the null hypothesis is true. In the null hypothesis, what's important to note is this fact, that the null hypothesis always contains the equal sign. What do I mean by the equal sign? So remember, we are making hypothesis claims on either any population parameter. So we are looking at mean, which is mu, population parameter, and proportion, the symbol I use is pi proportion, right? So H naught or the null hypothesis, we will always say, well, mu is either equal to some number, right? Or we can say mu is greater than or equal to some number, or we can say mu is less than or equal to some number. So you see, when I say this equal sign fact, what I'm really talking about is either it can be equal sign like this or an equal sign like this, because this is also saying greater than or equal, or I'm talking about this scenario where it's less than or equal. Whereas the alternative hypothesis, H1, is where you write mu is not equal to 30 because you don't contain the equal sign. In this scenario, you would say mu is less than 30 because null is greater than or equal to 30. H1 is mu less than 30. If you say H naught is mu less than or equal to 30, then H1 is simply mu greater than 30. Right? These are small things, but keep it in mind. So that's what I wanted to highlight here. This is what I say, it never contains the equal sign. So I've given you the examples. So what does it kind of mean to do a hypothesis test? So that's what I'm talking about in this particular, just a very basic example. So suppose the sample mean of age was x bar equal to 20, and then I'm claiming that the mean population age is actually 50. Now you see this 20 is significantly lower than a claim that I'm making, which is that the population age is 50. Right. So if the null hypothesis was true, so the null hypothesis is mu h naught mu equal to 50. Mu is the mean average age, the mean age of 50. The probability of getting such a different sample mean, the probability of getting that is very small because it's quite far away. So you can actually reject the null hypothesis. That is, you can reject the claim that you're making that H naught, the population mean is 50. But there's a problem. How do we say, it's very small? How do we reject it? That's the key thing, because visually, what we are saying is this. We are claiming that the population mean is 50. So that is H naught. However, when we take a sample and we look at it, the sample gives out an average age of 20. So then we have to have some parameter or some threshold value to tell us this 20 is too far away from the claim that we are making. So therefore, the claim we are making might be incorrect, right? So that's the question we have to ask. How far is far enough to reject H naught? So in order to do that, we come up with something called critical values. Sorry about that. So we come up with something called critical values. So um, if I were to draw that, so we are looking at normal distributions. Um, Standard normal distribution, you have 0 here. The axis over here is Z. And we have to figure out a critical value on either side. These are two critical values, because from those two critical values, we can develop a region, right? So we are developing a region this region more than the critical value and this region less than the critical value. These are two regions where we reject our claim, reject our claim H0. However, in this middle region, we accept our claim, right? So we call this region of rejection. We call this region of rejection, and the middle region, we call it the region of non-rejection. That's what I mentioned here, region of non-rejection. And on the either side of the critical values, we had the region of rejection. Rejecting what? The claim. What is the claim? H naught. H naught claim could be either on population mean or population proportion, because that's what we're looking at. So you'll understand it further when we look at a few examples. On errors, I'll just quickly mention what the two types of errors are. There are two types of errors in hypothesis testing. One is called the type 1 error, and the other one is called the type 2 error. Type 1 error is an error where you reject a true null hypothesis. That's what I mentioned here. You're rejecting a true null hypothesis. So the null hypothesis, the claim that you're making is actually true, but what this error is saying is you actually reject it. So that's a type 1 error, and that's a critical error, because in the field of medicine, in economic policy, um, you're trying to test something and that is actually true, but your test results give you that particular thing is false. So that's a very dangerous type of error, and the most dangerous type of error. And then we have something called the type 2 error, where you actually fail to reject a false null hypothesis. So null hypothesis is H naught. In type 1, you reject a true H naught. In type 2, you fail to reject a false H naught. That's what we are saying. So on a tabular format, you have the decision of either you do not reject H naught or you reject H naught. On the other side, you have H naught is true, H naught is false. So if H naught is true, and you don't reject H naught, there is no error, all good. But if H naught is false and you still don't reject H naught, that's called a type 2 error, because it's false and you're not rejecting it. If H naught is true and you reject the H naught, that is a type 1 error. If H naught is false and you reject it, no error at all. That's fine. Right? So these are the two types of errors. I wouldn't go into it in detail, but I will skip to the hypothesis test for mean. So similar to the last lecture on confidence intervals, we divide this hypothesis testing. Remember, we are only testing for one sample. So we have hypothesis testing for mean and proportions, just like the confidence interval lecture. And just like the confidence interval lecture, under hypothesis testing for mean, you have two sections again. When your population standard deviation is known and when your population standard deviation is unknown, right? So when your population standard deviation is known, the equation that we are using, the distribution table that we're going to use is the Z test. When it's unknown, we will use the t test. So let's dive right in. In the case of population standard deviation being known, when we are looking at the Z test, what is the test statistic that we're going to use? It's the Z test statistic, x bar minus mu sigma over root n. And you have seen this before, right? So the test statistic that we're going to use is that we call it statistic equals to x bar minus mu divided by sigma over root n. So what we are going to try and see is if the test statistic, whatever we calculate over here, falls in that rejection region that I showed you, these two regions, the rejection region, then we say we reject H naught. But if your test statistic, so if, for example, if your Z statistic falls either here or falls somewhere over here, you reject your H naught. But if your test statistic, whatever you calculate, falls somewhere in this region, okay, or this region, then we say that we accept our H naught. We don't reject our H naught. So that's the main thing that we're using. Um, so if we go to a quick example of how this whole thing works out, okay, it's a very basic one. So we are asked to test the claim that the true mean diameter of a manufactured bolt is 30 millimeters. So we are asked to check that H naught mu is equal to 30. Then I know H1 is mu not equal to 30. So I write those two things down. Then what else is given? We'll be told confidence interval will be given. So let's assume 95% confidence level. So if you're told 95% confidence level, that is 1 minus alpha is 0.95. So therefore alpha is 0.05. And if you are told that the sample size is, let's say, 100, and assume sigma is also given. So suppose sigma is given as 0.8. So 0.8. So that means we know we are going to use the Z test over here. So therefore the Z value of Z alpha over 2, because we are looking at a two-tailed test, right? Why are we looking at a two-tailed test? I'll come to that a little later. So here we simply know it's plus or minus 1.96. If you want, you can go to the table and also check it, which we did before, 0.025. It's 1.96 plus or minus, right? So then we go on to calculate the Z test statistic. So assume X bar, the sample mean is also given 29.84. So Z test statistics is X bar minus mu divided by sigma over root n. What is X bar? 29.84 minus what is mu? We are claiming it to be 30 divided by sigma is given 0.8 divided by sample size is 100. Don't forget the square root. So here you will get the Z test statistic as negative 2.0. Okay. Now you also have the Z critical value, which is that threshold value which you calculated as this plus or minus 1.96. So basically what we are doing is comparing these two values. We are comparing the Z test statistic against the Z critical value, because on the graph we have the same axis, which is the Z axis. Sorry, there's a small, okay. We have the same Z axis. We are looking at a standard normal distribution with mean 0, because in a standard normal distribution mean is 0, and we have figured out the two critical values for this level of confidence, 95% confidence level. The critical levels are on either side, negative 1.96 and positive 1.96. That's the Z critical value. Z critical. That's like the threshold value to determine whether we are going to accept or reject H naught. Then we go and place, okay, where is our Z test statistic, which is negative 0.20. So negative 0.20 is 2.0 is somewhere over here. So that is our Z test statistic, Z stat. So you see that the Z test statistic is beyond your critical value, because these two regions are your rejection regions. So therefore, you'd say because your Z test statistic, Z stat is less than your critical value, you would say you reject your H naught, right? So that's the visualization over here, right? So that's what I've given. So essentially, what you're trying to do always is comparing these two values, a critical value against the test statistic value, and you draw the visualization so that it's easier because when you draw it, you know, okay, beyond your two critical values on this side and on this side, if it's a two-tail test, because this is a two tails, there are two tails to it. It's a rejection region. Everything in between, that is over here, is where you accept. So in this case, our Z test statistic is beyond the Z critical value on the negative side. So we say that we reject it, reject H naught. But what does that mean? We don't stop here. We also say we reject the null hypothesis and conclude that there is sufficient evidence that the mean diameter of manufactured bolt is not equal to 30. Because what did our H naught say? We claim that mu is equal to 30, but now we are rejecting it. Why is that? Because we have sufficient evidence to say that the uh, population mean of the manufactured bolt is not equal to 30, and there's something missing here, which I haven't written, at 95% confidence level, because all of these calculations were made assuming a 95% confidence level. And that is very important to note because uh, if you change your confidence level to a significant variation, you may get a different value. Why is that? Because assume you change your confidence level such that your Z critical value goes beyond this negative point to somewhere over here. Then suddenly, because your Z critical value is far beyond your Z stat value, your test statistic value is not rejected because it's not in the rejection region anymore. So, depending on your confidence level, you calculate your two critical values, the two threshold values, and those two threshold values can either go this way or that way, depending on what the confidence level that you're selecting. So it's very important to say that yes, you're rejecting the hypothesis, and you say it's sufficient. There is sufficient evidence that this mean value of the bolt is not equal to 30. But you must not forget to say you must include at which confidence level. So in this case, it's 95% confidence level. So um, let's try this particular example as well on this e-commerce example. Okay, what is it saying? So it's saying an e-commerce company claims that its average delivery time for online orders is 5 days. Okay, so average delivery time, let's call it mu, 5 days. That's the claim. So alternative hypothesis is it's not equal to 5 days. Now, something that I told you that I'll mention, how do we figure out whether it's a two-tail test or one-tail test is by looking at your alternative hypothesis. Why is that? Because when you say mu is not equal to 5, what are the two possible scenarios? There are two possible scenarios. Either mu can be less than 5 or mu can be greater than 5. So there are two possible scenarios. Hence why we are testing for two regions, either less than 5 region or more than 5 region. right? But there can be scenarios in the definition that I gave right at the very beginning over here. So something like this. This and this is what we call the one tail test, right? These are one tail tests. So, for example, the last one, this one is what we call the upper tail test because we're only checking whether mu is greater than 30 or not. Here, it's called a lower tail test because we are checking whether mu is less than 30. So, we are looking at the alternative hypothesis and then determining whether it's a one tail or a two tail test. And that's important because when you're looking at the distribution tables, it's important, right? Get rid of these visualizations, right? So H naught, H1, that's done. However, some customers have complained that the deliveries are taking longer than expected. To investigate this claim, or the claim was that mu is equal to 5. A market research team decides to conduct a hypothesis test to determine whether the true average time differs from 5 days. The company assumes standard deviation of delivery times is known to be 1.2 days, so sigma is known, 1.2 days. A random sample of 64 recent orders is selected, and the sample mean delivery time x bar is 5.3 days, and a significance level of 0.05. So they're assuming 95% confidence interval, confidence level. So first and foremost, what we had to do? We had to compare two things: the Z test statistic versus the Z critical value in order to arrive at a decision. So first, let's calculate the Z test statistic, which is x bar minus mu. Sigma is known, so sigma over root 10. X bar is 5.3. Mu is claimed to be 5. Divided by sigma is 1.2. Divided by n is 64. Don't forget the square root of that. So the Z test statistic, I think you will get as 2. Then we check the Z critical value. That is Z alpha divided by 2. Why is it alpha divided by 2? Because it's a two-tail test. Because we determine it's a two-tail test by looking at this alternative hypothesis. If it's a two-tail test, we have to divide alpha by 2. Why is that? Because on the visualization like this, we are trying to figure out the critical values. So this region over here is the non-rejection region, right? And these two regions over here are the rejection regions. So this middle part is 1 minus alpha. Therefore, the remaining alpha is divided into two regions, alpha divided by 2. Hence why we look at whether it's a two-tail test or not. Because if it's a two-tail test, we check Z alpha over 2, which is plus or minus 1.96. Now what do? We compare these two values. So in our visualization, I'll draw it again. I'll use different colors for the critical values. So negative 1.96, positive 1.96. Now our Z test statistic is what? 2. So definitely you see that the Z test statistic is greater than the Z critical value because it's in this rejection region. So we therefore say that uh, there is statistical evidence to suggest that the average delivery time is different from 5 days because we are rejecting the claim H naught. So there is evidence to say that average delivery time is actually different from 5 days. So that's what we do, right? So more or less the same thing, but the small mistakes can happen. What one small mistake is not looking at the right table, whether you look at the Z table, T table, or F table. Another mistake that you can make is actually over here, whether you're choosing alpha or alpha divided by 2. You choose alpha divided by 2 if it's a two-tailed test. How do you figure out it's a two-tailed test? By looking at the alternative hypothesis, right? So here mu not equal to 5 means mu is either less than 5 or mu is greater than 5. So it's a two-tailed test. You select alpha only over here, alpha, if it's a one-tailed test. What's a one-tailed test? It's scenario of what I explained before. These scenarios. These two scenarios are examples of one-tailed test, because you look at the alternative hypothesis H1, either mu is less than 30, that's the lower tail test. This over here is a upper tail test, mu greater than 30. So that's another place, the second place you can make a mistake. Other than for that, what you're basically doing is comparing two values, right? So you're basically comparing the Z test statistic against the Z critical value. So I also talk about another way of calculating this, but I'll not go into that, but at a very high level. So what did we do to come at this particular conclusion to reject H0? We compared the Z values, that is the values on this particular axis, right? Because all of this is on the Z axis. So we compared values on the Z axis, the Z critical value and the Z test statistic. Arriving at this conclusion is actually not looking at the Z values, but by looking at the probability values. Why is that? Because whatever that I colored over here, these are all probability values, right? Because this is a standard normal distribution. So we can compare the probability value. So we calculate something called a p-value for the, we calculate a p-value for the Z test statistic that we calculated. So for example, the Z test statistic that we got was plus 2, right? So we go to the Z table, we look at where plus 2 is, plus 2 Z value, where is it? Over here. So that gives me this probability value, 0.97725, right? And then I compare that value with the alpha value, right? That's what I do when comparing, when this in the second approach. And how do you arrive at a decision? If the calculated p-value is less than alpha, we say we reject H0. If the calculated p-value is greater than or equal to alpha, we say we do not reject H0. So that's what I've done for the same example. Um, so I don't think we need to go into that. I think keeping it at one method is better. This is just a second approach because I just wanted to highlight what we do. So in our first method, we are comparing the values on this axis. In the second method, what we are doing is comparing the probability values. That's the regions covered and arriving at a decision. Right. All of this that we did before was for what? We were calculating hypothesis. We were doing hypothesis testing for one sample test. For the mean, we were looking at. We were looking at the mean. Don't forget test. We are looking at only one sample, and in that we were looking at mean. We are yet to look at proportions. Under mean, what we were talking up to now was when sigma is known. Next, we have to look at when sigma is unknown, right? So this is the next part of the this thing. So we'll look at sigma unknown and then we'll take a quick break. So we'll first look at sigma unknown. So the practical scenario we all have is that the population standard deviation is not known. And for this also, we calculate a test statistic. In this case, we calculate the t test statistic. Why is that? Because we are using the t distribution when sigma is not known. And we already know this test statistic, x bar minus mu divided by s over root n. We're not using sigma anymore because sigma is not known. And because sigma is not known, we are approximating it using the sample standard deviation. So S is what? S is the sample standard deviation. Right. So now we moved from the Z distribution, which we did before, to what? To the T distribution. Right. So when sigma is unknown, we go to the T distribution. So make sure that you look at the correct distribution table. Right. So uh, let's look at an example. What does this say? The average cost of a hotel room, we are still looking at mean, so that's why we're looking at averages. The average cost of a hotel room in New York is said to be $168. Okay, that's the claim. Claim is we are saying it's $168. Then the alternative is it's not equal to $168. Okay, this quickly tells me it's the true tell test. I note it down before I forget. To determine if this is true, a random sample of 25 hotels, okay, n is 25, is taken and resulted in an x bar. That's the sample mean, 172.50, and a sample standard deviation of 15.40. Alpha is given to be 0.05. So we are talking about a 95% confidence level. Confidence level. So these are things I quickly note down when the example is given. I think you have to determine if this particular claim is true or not. Right. So how do you go about doing this? So I know that it's a sample standard deviation that's given. So I have to look at the sigma unknown scenario. So I have to first look at the t-test statistic x bar minus mu s over root n. What is x bar? 172.50. What is the mu that we are claiming? 168 divided by what is s? 15.40 divided by what's the sample size? Square root of 25. So the t-test statistic that I would get is 1.46. Now I had to compare this t-test statistic against what? I had to compare this t-test statistic against the t critical value. Now, when it's a t distribution, don't forget you have something called degrees of freedom, and you won't forget it. Why? Because even if you look at the t distribution table, you have it, right? You have the degrees of freedom. So you can't forget it if you look at the right table. So how do we write this down? The T critical value is T alpha divided by 2. Why is it alpha divided by 2? Because I noted that it's a two-tailed test, comma, the degrees of freedom. Those are the two variables that we are looking at. So what is alpha divided by 2? What is alpha? 0.05. So alpha divided by 2 is 0.025. What is the degrees of freedom? Degrees of freedom is given by n minus 1. So degrees of freedom is n minus 1, which is 24. So what do I have to do? I have to go to the T table, look at the degrees of freedom 24, look at that particular row. Now it's a two-tailed test. I'm looking at 0.025, right? So I'm looking at 0.025 at a two-tailed test, right? So uh, my one tail value is then 0.025. So if it's a two-tailed test, I'm looking at a two-tailed test, one side of the value is 0.025, right? So hence why, if you're looking at the one tail value, it's 0.025. If it's a two tail value, you look at 0.05 because your alpha is 0.05 in a two tail test. Whatever it is, don't make that mistake. So my value over here is 2.064. So if I were to repeat what I said, if it was very confusing, uh, what did I do? So I had to check 24 degrees of freedom. Okay, that's the first thing. That's the row that I'm looking at. Then the column I had to look at is my alpha value is 0.05, right? So my alpha value is 0.05. However, it's a two-tailed test. Two-tail means if alpha is 0.05, then this over here is 0.025 because that's alpha divided by 2. On this side, it's also alpha divided by 2, which is 0.025. So what I'm looking at is this value. If it's a one tail, if you're looking at one side of this, it's 0.025. If not, if you want to consider it to be a two tail, it's alpha 0.05. Same way that you're looking at it. Okay, so make sure that you don't make a mistake there, because you don't go and look at a two tail of 0.025, which is not even there, right? You're looking at a two tail test with 0.05 alpha, which means one side of it is 0.025. So you go down and you figure out your T critical value, which is 2.064. That's your T critical value. What do you do now? Well, if you want, you can visualize it, because it's a little better if you do on your T graph, on your T distribution graph. So on either side, you have your T critical value minus 2.064 plus 2.064, and then you also have your T distribution here, which is 1.06. So you see that your T stat is less than your T critical value, because it's in this do not reject region. So therefore we say you do not reject your H naught. And that's what I've said. So what does that mean? You also have to write you don't reject H naught, which means there's insufficient evidence that true mean cost is actually different from $168. But you also have to say at 95% confidence level, because that's the confidence level at which you are making that claim. Now, from this, you can also look at a confidence interval, because that's what we did before. So in the case of a confidence interval for mu, what was the test statistic? X bar plus or minus S over root 10. So times, that's the standard deviation, times T alpha divided by 2 degrees of freedom. Let me write it properly. T alpha divided by 2 comma degrees of freedom times the standard error S over root 10. What was X bar? 172.5 plus or minus. What was T alpha divided by 2? So we got from our table 2.064. Here it's to four decimal points, but in our table it's only 3 decimal points. That's not a big issue. Times what is S? 15.4 divided by what is N? Sample size, this one. So then you would get mu confidence level, confidence interval of 178.86, 166.14. So what did we say? What was our claim? That mu is 168, right? So 168 is in this particular 168 is in this interval, 166 to 178. So we don't reject the null hypothesis at alpha 0.05, or you can say at 95% confidence level. So what I said before on the one tail test and the two tail testing. So one tail test, if your claim is mu greater than or equal to 3, you look at your H1 and mu less than 3, that's a lower tail test. That's one example of a one tail test. If your claim is mu less than or equal to 3, your H1 is mu greater than 3, you look at your H1, it's an upper tail test. That is also an example of a one tail test. So visually, what does it look like for a lower tail test? You're looking at this region only, because you're looking at that particular area. For an upper tail test, you're looking at this particular region. So see, it's alpha, right? It's not alpha divided by 2. That's where the change is coming. So in an example, we'll stop with this. In this example, because we're still under hypothesis testing for one sample test, mean, sigma unknown, because we looked at a two tail test example, right? Now we are looking at a one tail test example. So if we read this, a phone industry manager thinks that customer monthly cell phone bills have increased, and now average is over $52 per month. All right. So he's saying that it's over 52. So we have to have the equal sign. So over 52, H naught is mu less than or equal to 52. That's the key thing first that you note down, right? When you say over $52, it is H1. That person is getting paid H1. It is an example on tail, which means we are considering alpha only. Right. The company wishes to test this claim. So I think more information is given. Yeah. So we are asked to consider alpha 0. So that is actually 90% confidence level. And sample size we are told is 25. Okay. So what do? We have to calculate the t test statistic, which is x bar minus mu divided by s over root n. What is S? These have to be given. So S is 10. X bar is also given. 53.1. Mu is 52. 53.1. Mu is 52. We are assuming it to be 52. S is 10 divided by sample size of 25. So what do we get? We get the t-test statistic test 0.55. And then we compare it against our T critical value. T critical value. So the T critical value is alpha, comma, degrees of freedom, not alpha divided by 2, alpha, because it's a one-tail test. So what is alpha? Point the degree of freedom, comma, n minus 1, which is 24. So we go to our T-table test, T-table distribution. Degrees of freedom is 24. That keeps things easy. But our one tail is 0.10, right? So a 0.10. So a one tail is 0.10. So it's 1.318. It's one tail. So 0.10. So 1.318. And that's what we've calculated. So you see that the t-test statistic is less than the t critical value. So if you were to draw this, which I've done, but I'm just drawing it again, your critical value is somewhere over here, 1.318. 1.318. So this is your rejection region. This is only a upper tail test. Okay. And then your t test statistic is somewhere over here, 0.55. So because your t test statistic is less than your t critical value, you do not reject your H naught. So there is insufficient evidence that the mean bill is actually over $52 at 90% confidence level. At 90% confidence level. So we stop. So we stopped at hypothesis testing for mean, and we looked at two scenarios where the population standard deviation is known, where we use the Z distribution, and where when the population standard deviation is unknown, where we use the T distribution. And we also looked at two other things, whether whether the test is a two-tail test or a one-tail test. If it's a two-tail test, we had our alpha confidence level divided by 2. If it's a one-tail test, we only have alpha when we are looking at the distribution tables. So next, we move to hypothesis testing for proportions. Again, one sample only. So under hypothesis test for proportions, uh, we are looking at categorical variables, proportions. Just like before, no, I don't think I need to go into detail on the equations and all. So here, mu p equals the population proportions. Sigma p is pi 1 minus pi, but we use the Z test statistic. I think that's what's key here, that we're using the Z test statistic when we're looking at hypothesis test hypothesis testing. So we are looking at the Z test statistic, which is given by P, which is the sample proportion, minus pi, which is the population proportion, divided by pi, 1 minus pi over n, the square root of that. Okay, so let's look directly at an example. So what are we told? We are told a marketing company claims that it receives responses from 8% of those surveyed. To test this claim, a random sample of 500 were surveyed with 25 responses. So they're claiming H naught population proportion 0.08. Alternative hypothesis not equal to 0.08. Quickly, this is a two-tail test. Just note it down. We are told n is 500. Then sample proportion is 25 over 500. And we are told alpha is 0.05, which means 95% confidence level. So we have to calculate the Z test statistic and the Z critical value. We'll first go ahead and calculate the Z critical value because that's very straightforward. Z alpha divided by 2, which is 0.025. I don't have to look at the table even. Now I know it's plus or minus 1.96. Z test statistic, what is that? P minus pi divided by pi 1 minus pi over square root of n. What is P? P is 25 divided by 100 is point 0.05 is 5. So 0.05 minus pi is points. We are claiming it to be 0.08. 0.08, 1 minus 0.08 divided by sample size of 500. So this will give me a value of negative 2.47. So what are we comparing? We are going to compare this value against this Z critical value. So if we visualize it, remember it's the Z value, Z distribution, standard normal distribution. Our two critical values, 1.96 and plus 1. Where is our test statistic? Is somewhere over here, which is negative 2.47, right? So this is in our negative 2.47 is in our rejection region. So we say the Z stat is less than the Z critical and we reject our H naught at what was the confidence level? 95% level. Actually mean, so there is sufficient evidence to reject the company's claim of 8% response rate at 95% confidence level. So more or less, like I said, it's a pattern. It's a mechanical pattern. The changes that happen are the distribution, the two tail or one tail, and the equations used. So you just have to figure out whether it's a proportion or a mean. If it's mean, whether sigma is given or not given. If it's given, you use the Z distribution. Then you check whether it's a two tail or one tail. If it's not given, it's a T distribution. Check with, and degrees of freedom is also there. Then check whether it's a two tail or one tail. You have the appropriate equation. If it's a proportion, it's a Z distribution. Check whether it's two tail or one tail. And that's it. And check whether you're using the right equation. So that brings us to an end of hypothesis testing for one sample test. So now we come to hypothesis test, the next part, hypothesis testing. Now two samples. Now we come to bit more complex area, which is the hypothesis testing for two sample test. Even this lecture is already recorded and uploaded, and please remember I already have given uh, the revision one is also uploaded from last year, so I've made it available, made it visible for all of you all. Just make sure that you go through it, because in that I make the particular calculations as well. So just make sure that you go through it, just so that you're familiar with how to answer these questions. Right. So hypothesis testing for two sample tests, we have four sections, but we are mainly looking at three areas. Just like before, we are going to look at mean. We're going to look at proportion, population, again, population mean, population proportion. In addition to that, we are going to look at population variance. Now, this is new. Now, under mean, we have two main areas. Now, remember, we are looking at two samples. Earlier, we only looked at a one particular sample. So, when we are looking at two samples, those two samples can be independent of each other, or those two samples can be related. So why do I say related? Because let's say uh, the same sample, the same set of, let's say, um, people, they are given an intervention of like a training, and the same set of people before the training and after the training. We want to check whether there is a difference made by the training in output, whether there's a difference in output because of the training, same set of people. So that is a related sample. Then you have population proportion and population variance. Now, don't worry too much about how long the equations are and how big the equations are, because, like I said, the equations are given. In this particular lesson, the equations are quite complex. Just make sure that you identify the correct equation in the exam, and you simply substitute in the values and you put it on the calculator and you calculate the values. So, first, we'll look at the case of population mean testing hypothesis for two samples in the case of it being independent. So, in the case of it being independent, also, we are looking at two subdivisions. One is when sigma 1 and sigma 2, they are unknown, but they're equal. The other one is sigma 1 and sigma 2 are unknown, but they are not equal. So both cases we are looking at sigma 1, sigma 2 are unknown for both cases. But where it differs is, in one case, both are assumed to be equal. In another case, both are assumed to be not equal under the independent case of looking at hypothesis testing. So the point estimate now changes a little. Why is that? Because before we had only, in the case of population mean, our point estimate was what? Our point estimate was X bar, because we had only one sample. Now we have two samples and we're looking at whether there's a difference in between the two samples that we're testing. So hence why we take the population sample means of the two and we check whether there's a difference or no difference, or whether one is greater than the other or whether one is less than the other. So that's the idea. So we're basically testing these three scenarios over here. So one is, if you look at the lower tail test, the two tail test. So either we say both are same, because remember we are making claims about the population. So the two population means in the two samples are the same. Alternative hypothesis is no, two populations in the two samples are different, because it's not equal to zero. Not equal to zero means mu1 is not equal to mu2. In the two, so these are two. Now these two cases, the first two cases are what? These are one tail test cases. So in the one tail test, you have the lower tail test. How do you know whether it's a lower tail? You look at the alternative hypothesis. Mu1 minus mu2 is less than zero. What does that mean? that mu1 is less than mu2. In the upper tail test, what is it? You look at the alternative, mu1 minus mu2 is greater than 0. So which means mu1 is greater than mu2. So these are the three types of tests that we are going to do. And how does it look like visually? Remember, in a two-tail test, uh, you're looking at alpha divided by 2. In a one-tail test, whether it's upper tail or lower tail, you're looking at alpha. That is very important to keep in mind. Now, we are using the t-test statistic. Why are we using the t-test statistic? Because in both these cases, sigma 1 and sigma 2 is unknown. So if they're unknown, we use the t statistic, right? Or the t distribution is what we're going to use. So, like I said, the equations are pretty complex and pretty big, and you don't need to worry about remembering or any of these equations. There's no point. So here, like I said again, on the iPad, it's not showing up, but in the normal presentation, it does because I'm checking my computer as well, and it showcases. So if you're checking on your computer, it should show. Um, Now, in the t-test statistic, the the equation that we're using, check your right hand side what I'm writing, x1 bar minus x2 bar minus mu1 minus mu2 divided by sp squared divided by n1 plus sp squared divided by n2, the square root of that. This is the test statistic that we are going to use when sigma 1 and sigma 2 are equal in the independent case. So this is when independent and sigma 1 equals to sigma 2. In that particular case, this is the t-test statistic. Now, let's look at some comparables. Now, before, when sigma was unknown in our hypothesis test for one sample, what did we use? T-stat, x bar minus mu divided by sigma over root 10, right? So, isn't this somewhat similar? If you look at this part, now you have x1 bar minus x2 bar. Why is there x1 bar minus x2 bar? Because there are two samples and you're looking at a difference. In this part of mu, you have similarly mu1 minus mu2. You're looking at a difference. This part is a little different. Here we have something called sp squared divided by n1 because you have one sample size and you have two sample sizes. Two samples, one has n1 sample size, the second one has an n2 sample size. The only difference now is what is called this pooled variance. That is the only difference, and you need to calculate that separately. How do you calculate that? That is given by this particular equation. What is it? N1 minus 1 times S1 squared, which is the sample's variance of the first sample, plus N2 minus 1 minus 1 times S2 squared, which is the sample variance of the second sample, divided by N1 minus 1 plus N2 minus 1. So first you calculate this pool variance, go and substitute it here to calculate the t-test statistic. Because we are calculating a t-test statistic, we have something called degrees of freedom, which in this case is n1 plus n2 minus 2. Because in our one sample case, what was the t-test? What was the degrees of freedom? N minus 1. But here we have two samples. So we add the two samples together, the sample sizes together, and you deduct 2. So with that, the confidence interval can also be calculated. So how do we calculate the confidence interval? Confidence interval for what? Mu1 minus mu2, because we're looking at the difference of these two population means. So that is given by point estimate x1 bar minus x2 bar. That's the point estimate, plus or minus t alpha divided by 2. Why is t? Because sigma 1 and sigma 2 are not known. times sp squared 1 over n1 plus 1 over n2, the whole thing square root. That's the confidence interval. Right, let's apply this. Let's look at an example. So we are told um, that you are a financial analyst. You're a financial analyst, um, and is there a difference? Okay, is there a difference? Now look at the question. Is there a difference in dividend yield between the stocks listed on NYSE and NASDAQ? Oh, so that tells me when I'm given this question, we're looking at two samples, right? So we're looking at two samples. So it's a hypothesis test for two samples, and they're asking for is there a difference in yield between these two samples, right? So what do we have to do? Is there a difference between the mean yield, right? They're asking whether this is equal to 0 or whether there's a difference between the two, right? That is what they're asking. So I quickly write that down first because that is important. H naught, which is my null hypothesis, mu1 minus mu2 equals to 0. Once mu2 does not equal to 0, which means mu1 and mu2 are different. So from this, I figure out it's a two-tail test. I just write it down so that I don't forget. Then I write down N1. So I'm going to take NYSE as N1 as 1, the first sample, and NASDAQ as the second sample. So N1, the sample size is 21. N2 is the sample size of NASDAQ, 25. Sample means are given X1 3.27, X2 bar 2.53. Sample standard deviation is also given. S1 is given 1.30, S2 is given 1.16. Right. So now what do? I have to calculate two things, right? The t test statistic and the t critical value. That's what I have to do. So what is the equation for the t test statistic? So it's given, it'll be given, but x1 bar minus x2 bar minus mu1 minus mu2 divided by s t square divided to whole thing squared. So before I calculate this, I need to figure out what sp squared value is. How do we calculate sp squared? N1 minus 1 times s1 squared plus n2 minus 1 times s2 squared. I'm just simply writing down the equation which is given. N1 minus 1 plus N2 minus 1. Now let me substitute in the values correctly. That is where you can go wrong. 21 minus 1. S1 squared is 1.3 squared plus N2 is what? 25. 25 minus 1. What is S2 squared? 1.16 squared divided by, this is a multiplication, divided by N1 a 25 minus 1 plus, 21 minus 1 plus 25 minus 1. So this will give me a value of, if you just put it into the calculator, 1.5021. Now I go and calculate my t-test statistic. So x1 bar minus x2 bar, what is that? 3.27 minus 2.53 minus mu1 minus mu2. I'm claiming there is no difference, so let's assume it's 0, divided by sp squared, 1.5021 is sp squared, divided by n1 is 21 plus sp squared 1.5021 divided by 25. And where students go wrong very easily, you do all of this, you forget that you calculated sp squared and you suddenly go and square this also. So that is one area that you can go wrong. But remember, what do we have to put here? We are putting sp squared and we've calculated sp squared. Some students go and square this value 1.5021 and put it here. Because given the context of the time and the exam pressure and all that, right? So those are small mistakes that one can make. So here you will get the value of 2.40 t-test statistic. So now what do? We go and compare these two values, right? The t-test statistic, we compare it against what? The T critical value, where is that? So we have to figure that out. So the T critical value is T alpha divided by 2 degrees of freedom. Why is it alpha divided by 2? Because this is a two-tail test. What was alpha? 0.05. So 0.025. Degrees of freedom? Oh, we didn't calculate the degrees of freedom. So degrees of freedom is N1 plus N2 minus 2. N1 is 21 plus 25 minus, which is 44. Right? So because 46 minus 2, 44. So I had to calculate the T 0.025 comma 44, um, which is given in this particular table, T distribution table. So where is 44? Let me delete this first. Okay, degrees of freedom 44. That's what I'm interested in. Right, but remember, this particular table is calculating only the upper tail side. So 0.025 is what I'm looking at. Right. um, 0.025, because it's only one side we're looking at in this table, which gives me the value of 2.015. 2.015. So now what do? I just draw the distributional graph because it's easier for the examiner and for yourself. And then you note down the t test statistic, which is T critical values, negative 2.105 plus 2.105. Where is the T test statistic? 2.04, slightly above, right? 2.040, right? Slightly above, still in that rejection region, is the rejection region. So you see that the T statistic is greater than the T critical value. So we unfortunately have to reject H naught at what level? At 95% confidence level. So remember, 95% confidence level was different. Uh, Critical value goes towards this side. Then this statistic that we calculate may have not been in that rejection region. So hence why it's important to mention at what level. So that's what I've done here. And the conclusion is there is evidence of a difference in means at 95% confidence level. Right? So that's one particular example. Now, that's sigma 1 and sigma 2 are assumed to remember all of these things that we did was for the case of this particular case. Independent population means are independent from the two sample means. Two samples are independent, and from the two samples, the population standard deviations are equal. That's the case that we looked at. Next case is still we're looking at the two samples that are independent, but sigma 1 and sigma 2 are not equal. Because sigma 1 and sigma 2 were equal only, we calculated the pooled variance, sample variance, that SP squared. We were able to calculate this because we assumed that the two population standard deviations of the two samples were equal. But now we're saying a bit more of a more harder case where it's not equal. How do things change then? So if it's not equal, the t-test statistic changes a little bit. The numerator is fine. So it should be minus. Numerator is fine. What changes is the denominator, and significantly what changes is how you calculate the degrees of freedom. And that calculation becomes quite complicated, right? So I'm just noting it down here. Okay. So in the case of this particular case, your t-test statistic, your numerator is same. Point estimate x1 bar minus x2 bar minus mu1 minus mu2. In the denominator, now you don't have a pooled sample variance. Why don't you have a pooled sample variance? Because your two population standard deviations are different. So you calculate, you put in instead of that a sample stand variance of your first sample plus sample variance of your second sample, and you take the square root of all of that. Not much of a difference. So you're basically estimating because these two are not equal and anyway are not equal and they are unknown. But in the T, when we are having the T distribution, we calculate degrees of freedom. Now, in the case of sigma 1 equal to sigma 2, degrees of freedom was what? When sigma 1 equals to sigma 2, expression of freedom was n1 plus n2, um, n1 plus n2 minus 2, right? Simple enough. But when sigma 1 does not equal sigma 2, degrees of freedom is a whole other calculation. So that equation will also be given. But what is that equation saying? You take the sample variance of your first sample divided by n1. Add to that second sample variance divided by n2. And you square that whole thing. So that's your numerator. In your denominator, you take your first sample variance divided by n1, you square that, and you divide that by n1 minus 1. You plus S2 second sample variance divided by sample size, square that, n2 minus 1. So this whole thing is degrees of freedom when your sigma 1 and sigma 2 are not equal. So let's look at this given example. So in this particular example, what are they saying? Uh, the computer anxiety rating scale measures an individual's level of computer anxiety on a scale from 20, which is no anxiety, to 100, highest level of anxiety. Researchers at Miami University administers CARS to 172 business students. One of the objectives of the study was to determine whether there is a difference in the level of computer anxiety experienced, okay, whether there is a difference in the level of computer anxiety experienced by female and male business students. They found the following. So questions are, so these are the kind of questions you will get, similar kind of questions at an exam. At the 0.05 level of significance, is there evidence of a difference in the mean? Okay, so we are asked for whether there's a difference in the mean. So that's a quickly note down. They're asking whether this is equal with this h naught or whether this is not equal. So it's a two sample test because you anyway see two samples. So you quickly note that now. Computer anxiety experienced by female and male business students. So let's look at this. So I'm going to take males as my first sample, females as my second sample. Therefore, N1 is how much? 100, sample size of 100. N2 is 72. X1 bar is 40.26. X2 bar is 36.85. Standard deviation is given. S1 is given 13.35. S2 9.42. Another area that one can make an error, that you just note down that it's a variance that's given. No, it's not. It's a standard deviation and it's explicitly mentioned. Right. So what do we have to do? We have to compare two things, right? Simply, we have to compare T stat versus the T critical value. Okay. So that's what we have to do in order to arrive at a conclusion. Right. So mu2 equals to 0, which says that these two, there is no difference between the samples of males and females in this cars test. H1, mu1 minus mu2, not equal to 0. So basically, this is a two-tail test. Right. So let's calculate the t test statistic, right? So the t test statistic, how is it given? X1 bar minus X2 bar minus mu1 minus mu2 divided by S1 squared divided by N1 plus S2 squared divided by N2, the square root of that. So let's substitute in the values. X1 bar is what? 40.26 minus X2 bar is 36.85. We are claiming it's the difference is 0. And S1 squared is 13.35 squared divided by N1 is 100 plus S2 squared 9.42 squared divided by 72. Don't forget the square root. So the t-test statistic that you will get is 1.964 plus. Now we come to calculating the t critical value. So the t is the alpha is 0.05 and it's a two-tailed test. So it's t alpha divided by uh, t alpha divided by 2 comma degrees of freedom. What is alpha? It's 0.025 comma degrees of freedom. Now we have to separately calculate the degrees of freedom using that long equation. So I quickly just copy paste that equation properly from the equation page. Make sure that you copy paste it properly because these are small mistakes again because you're mentally tired as well, right? So plus S2 squared divided by N2 squared N2 minus 1. Now let me go and substitute in the values. So S1 squared is what? 13.35 squared divided by N1 is what? 100 plus S2 squared is what? 9.42 squared divided by 72. That whole thing squared divided by S1 squared 3.35 squared divided by 1 is 100 divided by N1 minus 1, 100 minus 1 plus S2 squared is 9.42 squared divided by 72. That whole thing squared divided by 72 minus 1. So if you put this into a calculator, you should get the answers degrees of freedom of about roughly approximately 150, right? So then what are you doing? Your critical value is 0.025 comma 150, right? Let's go to our t distribution table. So you scroll down, 150 is not there, but 140 and 180 are both there. So within that range, you can just see. Sorry. So within this range of 140 and 180 is what I'm looking at. What was 0.025, right? So 0.025. So it's either one of these values. So 150, the closest value is 140. So I'll take 1.977 because 150 is close to 140, 1.977. And you see that now what do? We compare this critical value against the t-stat value that we got. So the t-stat value was 1.964 and that is lower than the t critical value, which is 1.977 is what I calculated. So therefore, we do not reject not. So in this case, thankfully, everything is above. So 140, 180, it's 1.973, 1.977. So it's above this T stat value. So the T stat value is safely in the do not reject region, right? So that's another example. So we have to say at, like I said here, at the zero point zero 0.05 significance level, there is not enough statistical evidence to conclude that the male and female business students have different mean levels of computer anxiety. Right. So all of that we did for the cases of independent independent means. So we looked at sigma 1 equal to sigma 2 and the independent means, and sigma 1 not equal to sigma 2, and accordingly both cases use the t-test statistic. Only thing is here we had a pooled variance. Here the big equation was in the degrees of freedom. So that is the independent means case. Now we still under mean, because remember we are looking at hypothesis testing for two sample means. Now we looked at independent means, so that is done. Always don't forget the big picture. Now we are coming to related samples. These are our next section, related samples. So in the case of related samples, like I said, we are looking at the same sample, but we are giving it an intervention. One example of an intervention is the same sample is trained. So then before the training and after the training, whether there's a change in output level. So to analyze that, because it's the same sample, so it's a related sample, then the method is slightly different. So the test, the point estimate we are going to use is capital D, right? What is this capital D? It's called paired difference. It's called paired difference. What does it do? It simply takes each value from one sample and each corresponding value from the second sample, and it takes the difference. And once we calculate all of that, we can add up all these DIs for the full sample, and then we calculate this average of that difference, right, which is divided by n, 1 to n, and we calculate the standard deviation of that difference, paired difference variable. So di minus d bar whole thing squared, I going from 1 to n, we add it up, all up, divided by n minus 1. So the t-test statistic, we are using the t-test statistic here as well. Like I said, the point estimate is d bar. So t-test statistic is d bar minus our population mean difference divided by sample difference, which we calculated here, SD, divided by square root of n, because it's the same sample, n doesn't change, right? It's the same sample. The confidence interval is given by this, which is confidence interval for what? Confidence interval for mu d. Mu d is the mean sample difference, pair difference, which is the point estimate d bar plus or minus t alpha over 2, because we don't know the population standard deviation, SD over square root of n. So we'll look at an example, because that would make more sense of what this whole D thing is. So what is this pair difference? What is this? So assume you send your salespeople to a customer service training workshop. Has the training made a difference in the number of complaints? That's the output that we are looking at. Number of complaints, has it reduced after this particular training? So you collect the following data. You have how many salespersons? 5 salespersons. Number of complaints before the training for CB was 6. After the training, it has come down to 4. Before the training for TF, it was 20 complaints. Now it has come down to 6. Before the training for MH, it was 3 complaints. Now it has come down to 2. Before and after both, 0 for RK. Before the training for MO, it was 4. Now it has come down to 4. So what do? We calculate the difference after minus before. So we add them all up, right? It can be negative, positive, whatever, right? We get negative 21 when we add it all up. 4 minus 6 is minus 2. 6 minus 20 is minus 14. 2 minus 3 is minus 1. Likewise, we add it all up. Once we add it all up, we divide it. So negative 21 divided by 5, we get negative 4.2, which is D bar, right? Then what do? We calculate the standard deviation, SD, right? So when we calculate SD, for this, now this is the column that we are interested in against this column. SD is 5.67, right, for these variables. Then what do? We are asked whether there's a difference, made a difference in the uh, number of complaints, right? That's the question. So how do we write our H0 and H1? So our H0 is saying mu d equals to 0. That means there is no change. H1 is saying mu d is not equal to 0. That is, after the training, there is a change in the number of complaints. So remember, this is also, look at this, it's a two-tailed test, right? So it's a two-tailed test. Now, what do? Same as before. So assume alpha is given 0.01. We have calculated d bar, which is negative 0.4.2. We have calculated SD also, I think. Yes, SD was also calculated, 5.67, right? So then, in order to test whether there is a difference or not, we had to compare two things. What are those two things? The T test statistic versus the T critical value. I always write this down because it's very mechanical. These are the two things you have to compare. In the t test statistic, now you go to the equations page, make sure you get the right equation, which is d bar minus mu d divided by sd over square root of n. So what is d bar? Negative 4.2. Mu d, we are claiming it, there is no difference, so it's 0. SD we have calculated 5.67. How many, what's sample size? 5, so square root of 5. So you get the t test statistic as negative 1.66. Now, the t critical value. So that is t alpha divided by 2, comma, degrees of freedom. Alpha was 0.01, so alpha divided by 2 is what? 0.05, 0.005, right? Comma, degrees of freedom is what? Degrees of freedom is n minus 1, which is 5 minus 1, which is 4. So you go to the t table and then look at where 0.05 is, 0.005 and 4. So you get this value. So degrees of freedom is 4, 0.005, 4.604. So your T critical value is 4.604 and your T test statistic is minus 1.66. So if you graph this, you have your two critical values. What is that? Minus 4.604 plus 4.604. And what is your T test statistic value? It's safely inside this region, negative 1.66. So you say that you do not reject H0. That is, you're saying that there is insufficient evidence that there is significant change in the number of complaints. At 95, was it 95? No, I think it was 90. right? Yes, 5 was 0.01. So at 90% confidence level, that there is insufficient evidence that there is significant change in the number of complaints, right? So the test has not, the intervention hasn't worked out. So I've given another couple of examples there as well, so you can try it out. Then we move to the last area of today's section, which is looking at population proportion, hypothesis testing for population proportion. So we are looking at two samples, hypothesis testing. We're looking at two samples. Earlier we talked about mean, population mean. Now we are moving into population proportion. We have another part, which is population variance. We will not go into that today. We'll look at it next week. So in terms of population proportion, the point estimate is given by P1 minus P2. What was the point estimate in the population mean when, in the case of independent samples, it was, in the case of independent sample mean, point estimate was x1 bar minus x2 bar. In the case of related samples, in the related sample mean case, the point estimate was d bar, right? So those two, let's keep it to a side. In the case of proportions, the population point estimate is P1 minus P2. Give me 2 minutes. Sorry about that. So the point estimate in this case is P1 minus P2. So um, the estimation, the test statistic that we're going to use in this case, like before, in the earlier case of one sample, in the two sample case also we're going to use the Z test statistic. Similar to how it was written in the one sample case also, only difference is that we are looking at a difference between sample proportions minus difference between the population proportions led by the population proportion 1 minus p and into 1 over n1 plus 1 over n2. So what is this p bar? P bar is the what we called the pooled estimate, because there are two samples. You calculate the pooled estimate. You take the number of items from both samples x1 and x2, and you divide it by the sample size, the addition of the sample sizes of both samples. So if we look at an example to make things a little bit clearer, so we have they are asked, is there a significant difference between the proportion of men and the proportion of women? Okay, so now we know, we are asked, this is a two sample hypothesis test and it's for proportions. So I quickly note those things down. So I have to use the Z test statistic. Who will vote yes on proposition A? In a random sample, 36 out of 72 men, so that is 36 out of 72 men, I'll call that men as P1, 36 out of 72, or women, 5 out of 50. Is there, so we asked whether there's a difference between the proportion of men and the proportion of women. So what are we asked? So H naught is, there is no difference between the proportion of men and women in voting for this proposition A. H1 is, there is a difference in the men and women. So it's of voting for this proposition. There is a difference. So this is a two-tier test. I know that down, and I know these two things down as well, right? And then I had to calculate the pooled estimate. The pooled estimate, which is P bar, which is x1 plus x2 divided by n1 plus n2. So what is that? What is x1? X1 is 36. 36 out of 72 men were indicated they vote yes. No, so 36 is the number of men who voted yes. X2 is the number of women who voted yes, divided by 72 men in total plus 50 women in total. So my pooled estimate comes up to about 0.582. What I had to do is I had to calculate the two the test statistic, right? Because why is that? Because I had to ultimately compare the Z stat versus the Z critical value. Why is that? From this only I can come at a decision. So what is the Z statistic equation? So I go to the equations page, make sure that I copy correct equation. So I'm talking about proportions. So two samples and proportions. So this would be the equation that I note down. So what is P1 minus P2? P1 minus P2 is 36 divided by 72 minus 35 divided by 50 minus, we claim that there's no difference, so it's 0. P bar, we calculated it as 0.582 times 1 minus 0.582. 1 times 1 over n1 is 72 plus 1 over n2 is 50. Don't forget the square root. So the Z statistic value then I would get as negative 2.20. Fine. What is the alpha? 0.05 level. So Z critical is basically Z alpha over 2 because it's a two-test statistic, two-tail test. So it's 0.025. I already know. So I can visualize it also. Z 0, critical values negative 1.96, positive 1.96, and where is my is it test statistic? Somewhere over here, negative 2.20. So what does that mean? That tells me that I have to, it's in the rejection region, so I have to reject H naught. And what is the conclusion? That there is evidence of a difference in proportion who will vote yes between men and women. So that's the answer. But at what level? At 95% confidence level. And that is critical to understand. And then the confidence interval is basically P1 minus P2 plus or minus Z alpha over 2. P1 uh, P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. The confidence interval for the population. This is the population proportion difference in population proportion, right? So I given a couple of more examples over here. So what you can do is you can try those out. I will stop there for today because it was a lot of content thrown at you. So I think I'm recording this session. I will upload the whole thing on YouTube. Lesson by lesson also I have uploaded. Next week, right? Next week is, I think, the final week. I may have to take it online as well. I might not be available. Next week we'll have to look at I'll have to finish off this population variance part, and then we have to look at analysis of variance, which is also another lesson. Yeah, there we go. Analysis of variance is what we have to do next week, and this chi-square non-parametric. Of course, this chi-square non-parametric one, I won't focus on it too much. We'll go over it just for your information, a few areas that are important. But the key part is, I think, analysis of variance, which is an extension of the two sample test. So then we'll be done with our lessons.
Reminder of the reference book. Please make sure that you download this book and refer to it. There are many problems given in this particular book. All of these lessons are based on this particular book. And that is it for today. I would like you to do is go back in the video and make sure you watch it again and see which areas you do not understand. And hopefully once you watch it twice, 2 or 3 times, you'll get a basic understanding about. Thank you very much, and I hope you have a productive day.